followers of Neuro Takeaway. Today we are going to reveal our 6th NeuroQuiz. The final diagnosis was HEMS. HEMS is a recently described entity which stands for hypomyelination of early myelinating structures. And what is the role of myelin? Well, as we were taught in college, the main function of this structure is the propagation of the nerve impulse through the nodes of Ranvier. But there are other important functions, for example, the maintaining of axons, and the relationship between axons and myelin is bidirectional. For example, axons can provide glutamate to myelin, and myelin can provide with lactate to axons. But there are other players in this complex mechanism. For example, we have the oligodendrocyte precursor cells, which a process of very well regulated maturation evolve to the mature oligodendrocytes, which are the main component of myelin. And this mechanism may be vulnerable to different alterations. We also have the astrocytes, which are located close to the nodes of Ranvier, and they can provide with fatty acids and with the platelet-derived growth factor. Then we have the microglia that can provide insulin, growth factor 1, and finally we have the vessels through which come different important substances for the development of myelin, as glucose, iron, or thyroid hormones. And all this mechanism, as you know, is very well regulated. It evolves in a very predictable spatial and temporal pattern, and it can be very rapid. For example, it is estimated that it can reach 6,500-fold increase in surface area within hours. And based on this complex mechanism, Dr. van der Naap in 2017 came up with this classification, which is very important. She divided leukodystrophies in different groups. The first group is hypomyelination, and it is very important today because HEMS is a member of this group. Then we have the demyelination. For example, a metachromatic leukodystrophy is a very good example of this group. We have myelin vacuolation. For example, certain mitochondrial leukoencephalopathies can produce this pattern. We also have astrocytopathies, for example, Alexander disease. We have microgliopathies, for example, hereditary diffuse leukoencephalopathies with spheroids is a good example of this group. And we have also the leukoaxonopathies, which are diseases of the gray matter that secondarily affect white matter. For example, lipofuscinosis is a good example of this group. And finally, we have the vasculopathies, leukovasculopathies, CADASIL, CARASAL. There are many vascular disorders that can affect white matter. So this is a very interesting classification, and I think that it will allow the inclusion of more and more diseases that will appear within each of these groups. In 1920, a neuropathologist and psychiatrist of Germany in Leipzig, Professor Paul Flechsig, demonstrated the process of myelination in infants and in fetuses. And he showed that this is a very tightly regulated in space and time process. As you can see, the direction of this process goes from caudal to rostral, central to peripheral, and dorsal to ventral direction. So this process can be nowadays very well shown with MR. MR is very sensitive to water, and water is less and less prevalent during the process of myelination, because there is a compaction of these loose wrappings that are formed at the beginning. On T1 we see a progressive hyperintensity in the white matter, and on T2 we see a progressive hypointensity. This process ends earlier on T1 because this sequence is more sensitive to loose myelin, and it ends around the age of 9 or 10 months, and on T2 it ends around 2 years. There are some concepts that we have to be aware of in order not to get confused with them. The first one is primary hypomyelination. This is the first group of Van der Naap classification, and it is the one that Herms belongs of. This group, the definition of hypomyelination is a permanent and significant deficit in the deposition of myelin in the central nervous system. So it is recommended to perform a second study, a second MRI, at least 6 months later, in order to confirm this absence of progression in the process of myelination. And that's why it's tough to make this diagnosis during the first year of life. This doesn't mean that if we have the appropriate clinical context and we find hypomyelination, we can suspect certain disorders. The second concept is delayed hypomyelination or delay myelination. This delay myelination is a very non-specific diagnosis. It is associated with many disorders, including malnutrition, and there is a catch-up later in life. The third concept is secondary hypomyelination. This is another group of the Van der Naap classification, the leukoaxonal group. Refers to degeneration of myelin secondary to an axonal disorder, for example, neuronal ceroid lipofuscinosis. The third concept is the concept of incomplete myelination. As you know, there are some regions, for example, the peritrigonal white matter or the juxtacortical frontotemporal white matter, that last longer in developed incomplete their myelination process. So these areas can't be taken as hypomyelination because they are expectable in a certain degree up to the second decade of life, and they are located in very specific areas. There are a scale of hypomyelination, and we can detect it with the use of MRI. There are mild forms, moderate forms, and severe forms. In all of them, we get hyperintense signal intensity from the white matter, and that means absence or deficit in the deposition of myelin. But the difference between these forms is made with the T1 sequence. In the mild forms, there is hyperintensity, and that means normal myelination on T1. In the moderate forms, we find isointensity of the white matter on T1, and in the severe forms, there is hypointensity, that is no myelination on this sequence. And two important concepts are, first, as a whole, we can't predict the clinical state of a patient considering just MRI. But in a single disorder, yes, there is a correlation between the degree of hypomyelination and the clinical status. Up to 2011, half of the patients with hypomyelination remained without an etiologic diagnosis. But since then, there has been a huge improvement in this issue. At the beginning, we just knew about mutations of the most important protein, the structural protein of myelin, which is proteolipid protein, and about the myelin basic protein. Now, there are a lot of disorders, and this knowledge came from genetic studies, There are disorders of the mitochondria, of the lysosomals, disorders of other structural proteins are tubulins or light chain filaments. There are disorders of certain channels, for example, the connexins. There are disorders of the maturation of oligodendrocytes, etc., etc. I don't want to deepen in this topic, but I refer you to this very interesting paper by Patrick Malik, published last year. Here you have the most frequent etiologies of hypomyelination. On the left, the Pelizaeus-Merzbacher disorder or disease, which is secondary to duplication of PLP1 gene. Proteolipid protein is the most important structural protein of myelin. It represents around 50% of its structure, and that's why it is associated with a very severe form of hypomyelination. On the right, you have the second most frequent cause of hypomyelination, the 4H syndrome, which is secondary to mutations of polymerase R3A or R3B genes. And it is associated with very funny findings on MR as the preservation of myelination of the optic radiations, ventrolateral thalami, and medial lemnisci. And now let me make a historical digression. Professor Ludwig Merzbacher, who was a German neuropathologist and psychiatrist, described the pathological finding of his disease in 1908, many years after Professor Pelizaeus described the clinical findings of this disorder. But 2 years later, in 1910, Professor Merzbacher decided to move to a prosperous country. He was going through very tough economical times in Germany. He earned too little at the university, and he decided to move to a prosperous country of that time, Argentina. He came to Buenos Aires. He was named director of the Hospicio de las Mercedes, now Hospital Borda, the most important public institution of psychiatry of Buenos Aires. And he developed a very interesting career. He worked with Professor Jacob, who was here at that moment, and he studied a lot. Especially, he was very interested in the microglia, which now is so important. We know it is so important. Let's talk very briefly about HEMS. This entity was described for the first time by Dr. Marion Steenweg from the group of the Netherlands. They discovered several patients with the same imaging pattern. There was compromised, there was hypomyelination of early myelinating structures with relative preservation of the rest of the white matter. Years later, they discovered that the cause of this entity was a mutation in the PLP1 gene with affectation of the exon 3B or intron 3, which produced abnormal alternative splicing of the product of this gene. You know that PLP1 produces two isoforms, PLP and DM20. DM20 is very, very important in the earlier stages of myelination, and secondary to this mutation, there is an imbalance of the relative amounts of these isoforms. So this is very important because very frequently this alteration is neglected by the usual sequences, the usual panels, the next generation sequences, and the whole exome sequencing. So it's important for us as neuroradiologists to alert the clinicians about the presence of this imaging pattern so they can ask for a specific test to diagnose this entity. Regarding the clinical picture, It is very similar to the rest of the hypomyelinating processes. The patient comes with psychomotor delayed, with ataxia, with nystagmus, especially pendular nystagmus. There is relative preservation of cognition and very rarely epilepsy. The process usually starts during the first or second year of life, and it evolves very slowly. Well, we will talk about imaging in the next slides, but I would like to highlight here that very recently there have been some papers, some publications about new cases of this rare entity, and they described some changes in the evolution of the MRI pattern of this process, with myelination of some structures that at the beginning were hypomyelinated, and on the other side there was some compromise of other structures that at the beginning were not compromised. And now we can look again at the images of our patient. You have here the T2 sequence axial images that show very nicely the hyperintensity, the abnormal and subtle hyperintensity at the level of the medulla, at the level of the pons, especially at the dorsal part and caudal part of the pons, with preservation of the myelination of the central tegmental tracts. You can see as well the compromise of the ilios of the dentate nucleus, which are hyperintense on this sequence, allowing the detection of the dentate nuclei gray matter, which is unusual in a normal baby. And on the sagittal images you can see the normal myelination of the corpus callosum, which is unusual in a very severe hypomyelinating process. The last slide, you can see here the pattern at the supratentorial level with the typical trilaminar pattern of the plique, the posterior limb of the internal capsules. There is a hyperintense band, hypointense band, and another hyperintense band. All the cases of this entity have this pattern. And at the convexity, you can see the hypomyelination of the juxtacortical pericentral structures, white matter, which is another early myelinating area. And with this, I finish up with this presentation, and I would like to tell you that Neuro Takeaway has reached 1K subscribers, which is very encouraging, but at the same time entails a great deal of responsibility. So thank you for the support. See you next week. Bye bye.